Hello everyone, welcome to my channel Learn Physics with MPG. I am Dr. Mrityunjay Prasad Ghosh, currently working as an assistant professor at SR University, Warangal, Telangana, India. So today we are going to discuss some important topics related to magnetostatic. You know about the magnetostatic. Magnetostatics is a study of magnetic fields in a system where the currents are steady or steady current are flowing through the systems. Basically, the currents do not change with time or over time. Okay, so magnetostatic is a study of magnetic fields in several systems where steady current are flowing through the different systems, right? So if you take a system where steady current is flowing through the system, that is the current do not change or the current is constant over time, then if you want to study the magnetic field produced by the steady current, then this type of study is fall under the category of magnetostatic, right? So now we will discuss three important topics, that is Biot-Savart law, Ampere's law, and application of Biot-Savart law and Ampere's law. So let's start the discussion. So as we have discussed, we are going to understand the statement or concept of Biot-Savart law. We will discuss Ampere's law. We will go through the applications of Biot-Savart law and Ampere's law, and then we will solve some numerical problems based on Biot-Savart law and Ampere's law, right? So moving to the next slide. So what is the statement of Biot-Savart law, right? So here you can see that a current carrying wire, right? So this is the current carrying wire, right? Which is carrying a steady current I. Okay, and ideal is the small current element, or where dl is the length of the current element. So you need to calculate the magnetic field at any field point P due to this small current element ideal, right? So the distance of this point P where we need to calculate the magnetic field from the current carrying element is r, right? Or you can say it the radial vector r, that is the distance between the current carrying element, that is ideal, or the current element ideal, that is a small portion of this current carrying wire, right? So the distance between r is the distance between the current carrying element or the current element ideal and the field point P where we need to calculate the magnetic field B, right? Or a magnitude of the magnetic field B, or it is also called magnetic flux density or magnetic induction, right? So what is the magnitude of the magnetic field or magnetic flux density at the point P due to this small current carrying element or the current element ideal, right? Which is a small portion of this current carrying wire which is carrying a steady current I, right? Here the steady current I is flowing through this wire, that is the current is constant, so it doesn't change over time, right? So now the magnitude of the magnetic field at the field point, right? That is the field point, P is the field point around a steady current flowing through a conductor, right, is directly proportional to I dl sine theta, right? So the magnitude of the magnetic field due to this small current element IDL at a field point phi, which is situated at a distance r from this current elements, right? So the distance between the current element and the field point phi where we need to calculate the magnetic field is r, right? So the magnitude of the magnetic field due to this current element IDL, that is dB, is proportional to the current flowing through the wire or the flowing through the current element, right? So dB proportional to I, right? dB, that is the magnitude of the magnetic field at the field point P due to this current element, is also proportional to the current element or the length of the current element, that is dB is also proportional to dl, right? dB, that is the magnitude of magnetic field, is also proportional to the angle between the current element and the radial vector to the point P, right? This R is called also called the radial vector or the radius vector or the radial vector. That is, so theta is the angle between the current element, right, and the radial vector to the point P, right? So it is also proportional to the sine theta, right? dB, that is the magnitude of the magnetic field due to the small current element ideal, is proportional to the sine theta, where theta is the angle between this current element ideal and the radial vector to the point P, right, where we need to calculate the magnetic field due to this current carrying element or current element, right? So dB is proportional to I, dB is proportional to dl, that is the length of the current element, and dB is proportional to the sine theta, where theta is the angle between the current element and the radial vector to the point P, to the field point P, where we need to obtain the magnetic field due to this current carrying wire or current carrying element, right? The dB also inversely proportional to the square of distance between current element and the point P, right? So if R is the distance between the current element, that is ideal, and the point P where we need to calculate the magnetic field, right? So dB is inversely proportional to the square of distance, that is 1 by R square, square of distance between current element and the point P, right? So you can see that the R is the distance in between the current element and the field point P, where you need to calculate the magnetic field. So dB is inversely proportional to 1 by R square, right? So dB is proportional to I, the current flowing through the conductor or wire. dB is proportional to dl. dl is the length of the current carrying element or current element, and dB is proportional to sine theta, where theta is the angle between the current element and the radial vector radial vector r to the point P, right? Also dB is proportional to 1 by r square, that is the distance between the current element and the point P, right? So you can say that, taking all together, dB is proportional to I dl sine theta by r square, right? Hope it is clear now. So the dB, that is the magnitude of magnetic field at any field point due to the current carrying wire or the current element, that is ideal, is proportional to ideal sine theta by r square. So dB is proportional to ideal sine theta by r square. So let's move to the next slide. So you can say that is dB equal to k ideal sine theta by r square, right? Where k is called the proportionality constant. So dB is proportional to ideal sine theta by r square. So you can say that dB is equal to k ideal sine theta by r square, where k is the proportionality constant, right? For free phase, k attains the value mu0 divided by 4 pi, right? For free space or in vacuum, the proportionality constant k takes the value mu0 by 4 pi, right? Where mu0 is the permeability of free space or vacuum, right? Which is equal to 4 pi into 10 to the power minus 7 Weber per ampere meter, right? So what is permeability? So it's basically measures the ability of space or vacuum to support a magnetic field, right? So the magnetic permeability or the permeability of free space is basically measures the ability of free space or vacuum to support a magnetic field, right? So its value, that is mu naught or mu 0 equal to 4 pi into 10 to the power minus 7 Weber per ampere meter, right? So you can say that P equal to the proportionality constant K equal to mu 0 by 4 pi. So dB equal to mu 0 by 4 pi into I dl sin theta by r square, right? So this is equation number 6, which gives the magnitude of magnetic induction or magnetic field or magnetic flux density at a field point in a magnetic field, right? So hope it is clear now. So moving to the next slide. So we have already discussed the magnetic field generated by a steady current in a wire can be represented as dB equal to mu naught by 4 pi I dl sin theta by r square. This is the mathematical form of Biot-Savart law. So now we will solve a numerical problem based on Biot-Savart law. So let's solve the problem number 1, that is a current element of length 2 millimeter, right? We have discussed the current element, right? I dl, right, where I is the current and dl is the length of the current element, right? So a current element of length 2 millimeter carries 4 ampere current, right? So it placed at a distance 5 centimeter, okay, from a point, suppose P. You need to find out the magnetic field at that point, right, where the theta, which is the angle between the current element and the radial vector to the field point, which is theta, is given. Theta is equal to 90 degree, right? So we know the mathematical representation of Biot-Savart law, that is dB equal to mu naught by 4 pi I dl sin theta by r square, right? So theta is given, theta is 90 degrees. So sin 90 degree equal to 1, right? You know that sin, sin 90 degree equal to 1. We know that. So the length is given, the length of the current element is given, that is 2 millimeter. 2 millimeter means you need to convert it into meter, right? You need to convert this millimeter into meter. So it is equal to 2 into 10 to the power minus 3 meter, right? So dB equal to mu naught by 4 pi. We know that mu naught equal to 4 pi into 10 to the power minus 7. So mu naught by 4 pi is equal to 10 to the power minus 7 into I. I is 4 ampere, right? The length of the current element, that is dl, which is equal to 2 millimeter, means 2 into 10 to the power minus 3 meter. Okay. What is the distance between the current element and the field point P, where we need to calculate the magnetic field? That is 5 centimeter. 5 centimeter means 0.05 meter, right? So put all this value in this expression, then you will get the dB, that is the magnetic field, is 3.2 into 10 to the minus 7 Tesla, right? So we have calculated the magnetic field at the field point, which is equal to 3.2 into 10 to the minus 7 Tesla. Hope you understand the solution of this problem. So now moving to the next slide. So now we will discuss the Ampere's law, right? So what is the statement of Ampere's law? So Ampere's law states that the line integral of magnetic field intensity over a closed path is equal to the amount of current enclosed by the path, right? So the Ampere's law is basically state that the line integral of magnetic field intensity, where H is called the magnetic field intensity, right? Where B is called the magnetic flux density or the magnetic induction, right? So H is called magnetic field intensity, where B is called magnetic field or magnetic flux density or magnetic induction. So the line integral, you know the line integral, the line integral of magnetic field intensity. So the line integral of H, that is the magnetic field intensity over any closed path or the closed loop, is equal to the current that is enclosed by the path, right? So what is the mathematical form? That is the closed path C. What is the mathematical form? That is line integral of H dot dl is equal to I, right? So this is the integral form of Ampere's law, or you can express the Ampere's law in terms of magnetic field or magnetic flux density or magnetic induction, right? So in terms of magnetic flux density, what is the statement of Ampere's law? That is the line integral of magnetic induction or magnetic flux density over any closed path is equal to mu0 times the amount of current enclosed by the closed path, right? So here the line integral of magnetic flux density or magnetic field induction or magnetic induction over any closed path is equal to mu0 times the current enclosed by the closed path, right? So this is the line integral. So B dot dl, line integral of B dot dl is equal to mu naught I, right? Or you can say that this is another integral form of Ampere's law in terms of magnetic induction or magnetic flux density, right? So we know that the magnetic induction or magnetic flux density B equal to mu naught into magnetic field intensity, right? H. So this is the relation between B and H in a free space, right? Or in vacuum. So B equal to mu naught into H. So B is the magnetic field or magnetic flux density or magnetic induction, which is equal to mu naught, that is the permeability in free space or vacuum, into the magnetic field intensity, B equal to mu naught H. So this is the integral form of Ampere's law in terms of magnetic field intensity, and this is the integral form of Ampere's law in terms of magnetic induction or magnetic flux density, right? And the relation between the magnetic induction or magnetic flux density is B equal to mu naught H. Mu naught is permeability in free space, right? Which is 4 pi into 10 to the power minus 7 Weber per ampere meter. Okay, hope it is clear now. So moving to the next slide. So now we will discuss the integral form of Ampere's law, that is B dot dl equal to mu naught I enclosed, that is the current enclosed by the closed path, right? This is the integral form. So we will now derive the differential form of Ampere's law, right? So in terms of magnetic field density or the magnetic induction, the integral form of Ampere's law is line integral B dot dl equal to mu naught I enclosed. I enclosed is the current, right? That is closed by the, that is flowing in between the closed path, right? So the I enclosed, that is the current enclosed by the closed path, can be represented is J dot dA. dA is the area of the closed path or area of the conductor, and J is the current density, right? So I enclosed equal to J dot dA, right? So the current can be expressed in terms of current density. So the current enclosed by the closed path is equal to J dot dA, right? dA is the cross-sectional area of the conductor, right? So, or you can say that the area of the closed path, right? If the closed path is inside the conductor, right? So if this is a conductor, if the closed path is inside the conductor, then it is the area of the closed path, or if it is the outside of the conductor, suppose this is the closed path, then dA is the area or the cross-sectional area of the conductor, right? So this is the distance and this is the cross-sectional area, right? Which can be written as dA or A, right? So I enclosed equal to J dot dA. J is the current density, right? Current per area. This is called the current density. So we can replace the I enclosed, that is the current enclosed by the path, is B dot dl equal to mu naught J dot dA, right? So now we will apply the Stokes theorem. So Stokes theorem basically converts the line integral into the surface integral, right? So B dot dl equal to curl V into dA. This is the dot product, right? So B dot dl over a closed integral or the closed line C, which is equal to curl V dot dA, that is a surface integral, right? Surface integration. So it's basically convert the line integration into the surface integration, right? So B dot dl equal to curl V dot dA, right? So now replace B dot dl by curl V dot dA. So it is curl V dot dA equal to mu naught J dot dA, right? So for an arbitrary surface or for an arbitrary surface area, you can say that curl V equal to mu 0 J, where J is the current density. So this is the differential form of Ampere's law, right? So, or you can say in terms of magnetic field intensity or magnetic intensity, that is H, or in terms of magnetic field intensity, curl H equal to J, right? J is the current density, right? Current per area, right? So this is the differential form of Ampere's law in terms of magnetic intensity, right? Or magnetic field intensity, or in terms of magnetic flux density or magnetic field or magnetic induction, curl V equal to mu naught into J. So what is the relation between B and H? That is the magnetic flux intensity, flux density, and the magnetic intensity H, that is mu naught into H, right? You know the B and H both are vector quantity. Okay, this is the relation between B and H. So hope the differential form of Ampere's law is clear now. So moving to the next slide. So we know the statement of Ampere's law, that is the line integral of magnetic field or magnetic flux density around any closed path is equal to the net current enclosed by the path. Okay, the magnetic field or the magnetic field intensity here, right? Magnetic field intensity. So that is H. Here the statement is telling about H, not B, right? If it is B, then it will be the mu 0 time the current enclosed by the path, or if it is the magnetic field intensity, that is H, right? Then the line integral of the magnetic field intensity around any closed path is equal to the net current enclosed by the path, right? Or if it is the magnetic flux density, then the line integral of magnetic flux density around any closed path is equal to mu 0 times the current enclosed by the path, right? So this is the in terms of flux magnetic field intensity, right? So this is the integral form of Ampere's law. In terms of magnetic flux density or magnetic induction, this is the form of Ampere's law, right? And these are the differential form of Ampere's law in terms of magnetic flux density or magnetic induction or magnetic field, that is curl V equal to mu naught J, right? J is the current density, current per unit area, and this is the differential form of Ampere's law in terms of magnetic field intensity, that is curl H is equal to J, right? J is the current density. So hope it is clear now. So moving to the next slide. So now we will calculate the magnetic field intensity due to a infinitely long straight current carrying wire which carries a steady current I at any field point P, right? So we will calculate the magnetic field intensity at any field point P due to a infinitely long current carrying conductor, which is a state conductor, right? So suppose this is a infinitely long current carrying state conductor which carries a steady current I, right? So we need to calculate the magnetic field intensity at any field point P at a distance R from the infinitely long state conductor, right? Hope it is clear now. So we need to draw a circle of radius R, where R is the distance from the infinitely long steady conductor to the field point P, where we need to calculate the magnetic field intensity, right? So we draw a circle of radius R, right? At the center of the circle is here, that is within the conductor, right? So the center of this circular loop is within the conductor, that is the center O, right? So as per the Ampere's law in terms of magnetic field intensity, the Ampere law can be expressed in this mathematical form, right? This is the integral form of Ampere's law, that is H dot dl equal to I. I is the current enclosed by the closed path, right? So what is the closed path dl? That is 2 pi r, that is the periphery or circumference. The circumference of this circular loop is 2 pi r. So the line integral of dl will give you 2 pi r, that is the circumference of this circular loop of radius r, right? So h into 2 pi r equal to I. So you can easily calculate the magnetic field intensity H equal to I by 2 pi r, or in terms of magnetic field, or in terms of magnetic flux density or magnetic interaction, that is B equal to mu naught I divided by 2 pi r, right? The circumference of this circular loop, right? And we know the relation between B and H, that is B equal to mu naught B equal to mu naught H, right? So in terms of B, it is mu naught I by 2 pi r. So this is the magnetic field intensity or magnetic flux density due to an infinitely long state conductor which carries a steady current I, right? So this is the magnetic flux density or flux or magnetic field intensity, that is H or B at a distance R for this infinitely long state current carrying conductor which carries a steady current I. So hope it is clear now, right? So now moving to the next slide. So now we will solve a problem related to the Ampere's law, right? Basically the long current carrying wire. Okay, so the problem states that a long straight wire carries a current of 5 ampere, right? So let's consider it infinitely long steady current carrying conductor, right? So infinitely long steady current conductor, right? So a long straight wire carries a current of 5 ampere, right? So you need to find out the magnetic field at a distance 10 centimeter from the wire, right? So we know the formula, the magnetic field B equal to mu naught I by 2 pi r, right? So B is called the magnetic flux density or magnetic field or magnetic induction, right? Where H is called magnetic field intensity, right? So B equal to mu naught I by 2 pi r, right? Here I is given, I is the current flowing through the long straight wire, right? So I equal to 5 ampere. You need to calculate the magnetic field at a distance 10 centimeter. So you need to convert it into meter, right? So 10 centimeter is equal to 0.1 meter, right? So R equal to 0.1 meter. You know the value of mu naught, that is the permeability in free space or vacuum, that is 4 pi into 10 to the power minus 7 Weber per ampere meter, right? Weber per ampere meter. Okay. So this is the value of mu naught, that is the permeability in free space or vacuum. So put all the values in this expression, that is B equal to mu naught I by 2 pi r. So B equal to mu naught is 4 pi into 10 to the power minus 7, right? The current is 5 ampere into 5 divided by 2 pi r. So 2 pi into r is 0.1 meter in terms of meter. So it is given in centimeter, 10 centimeter. So in terms of meter, it is 0.1 meter. So 4 pi into 10 to the minus 7 into 5 divided by 2 pi into 0.1, right? So you will get 1 into 10 to the power minus 5 Tesla, right? So this is the magnetic field at that field point at a distance 10 centimeter from the wire. So the magnetic field B equal to 10 to the power minus 5 Tesla. So we have calculated the magnetic field at a distance 10 centimeter from the wire, which carries a current of 5 ampere, right? So what is the value of magnetic field? That is 10 to the power minus 5 Tesla, right? So hope you understood it and it is clear now. So now moving to the next slide. So let's discuss the application of Ampere's law. So Ampere's law is basically used to calculate the magnetic field around a long straight current carrying conductor. So we have already calculated the magnetic field B equal to mu naught I by 2 pi r. So it is also helpful to finding out, or it is helpful to find out the magnetic field inside a solenoid. You know about the solenoid. So the magnetic field inside a solenoid you can easily calculate by using Ampere's law, right? It is also used to determine the magnetic field inside a toroid, right? Also, this law, that is the Ampere's law, is helpful in designing the electrical devices like motor, transformer, inductors, right? So they are made of several conducting coils, right? So this law is helpful to understand the developed magnetic field when current is flowing through the coils, right? In motors, transformer and inductors, right? Or you can say the generator, right? In generator, motor, transformer and inductor. So you can easily calculate the magnetic field generated due to the steady state current by using Ampere's law. Okay, so this is also helpful. This Ampere's law also helpful in calculating the enclosed current if you know the magnetic field. If you know the value of magnetic field for a system, and if the steady current is flowing through the system, then you can apply Ampere's law to find out the steady state enclosed current or the steady current in the system, right? So you can calculate the steady current if you know the value of magnetic field for a system, right? So these are the application of Ampere's law. So thank you for your patience.